Welcome back. So we're going to learn about a technique called MIP mapping. And MIP mapping, don't worry about what MIP stands for. It's some kind of Latin or something or other. But it's basically a technique of solving this problem of when we have too much minification, our bilinear breaks down. So here's the idea. What if we pre-compute? We can pre-compute filtering with larger windows. How's that going to work? It's really clever, actually. Okay. So what we do is we look at it differently. Instead of pre-computing larger windows, let's pre-compute smaller textures. Okay. So let's pre-compute smaller textures. So this is how it works. So you can imagine we have this nice full-sized texture here, okay? And then what we do is we start by pre-computing, I should keep it green I guess, pre-computing a texture that's exactly a quarter of the size or half the size in each dimension. And what you do is when you pre-compute that, for every pixel in the smaller one, you take a 2x2 window, just like in our bilinear filtering, you do bilinear filtering to get that into that smaller one. So this is half the size, okay? And this uses a 2x2 window to make it. So you pre-compute that smaller version of the texture. And then what you do is when you're using your game, you use this, the big one, when you need the full size. Right? If you're stretching, if you're magnifying, for example, or you're minimizing just a little. But you're still bigger than half size. But if you're minimizing more and more, if minimizing to less than half the size, switch over to this one. You've already pre-computed it, okay? Now this is what's really cool about that. If I switch over to the smaller texture, and in this smaller texture, I'm going to use a 2x2 window because I'm using bilinear, no big deal. In fact, what you're doing is this maps back here to, it's a 2x2, but each pixel maps from a 2x2, right? So you're actually getting a 4x4 sampling of the original texture with your bilinear because you've already pre-computed that half size. So this effectively samples a 4x4 patch. And what's really cool about this is we just keep on going. Let's go half size again, right? So now I'm at a quarter size, or instead of a 4x4 patch, it's a 16x16. Let's do it again. Let's do it again, right? And again, all the way down to 1 pixel. Hey, Jim, didn't you say that powers of 2 for textures are really useful for certain things? Haha. I can half and half and half and half again, all the way down to the bottom without any rounding errors. So that's a really nice feature of sticking to power of 2 textures, okay? So, oops. Let's have a few notes. If we do this, what we get is we get more globally accurate. What I mean by that is you end up getting the feature of the whole texture and not just your 2x2 window, because as they get smaller and smaller, my patch sizes in the original get bigger and bigger and bigger, right? 16x16, 32x32, the patches get really big in effect. So you capture the average of the whole global window in that texture. So you get more globally accurate miniaturized textures. So, and then the last thing I'll mention in case it's not obvious, what we do is as we're drawing, we choose the level based on minification. Cool. So as we're rasterizing, we realize how much we're having to miniaturize. We use we use that information to choose our mip-map level. So let's go look at some slides. Okay, so here's an example of what a mip-map looks like. As you can see, it takes 1.5 times the memory, and there's actually space in there you can fill with other things. It doesn't take double the memory. Here's a mip-map, smaller, half, 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 again, all the way down, right? So that's a mip-map. And here's an example. Previously we had nearest neighbor with bilinear, and now if we add mip-maps into the mix, nearest neighbor here, bilinear, and you can see, wow, I keep that coherence. You start to get a bit of breakdown, a bit of Moyer pattern in some small spots, but you keep that coherence all the way down. You don't get any of these funny artifacts where it doesn't really look like a checker floor anymore. And if you did this in an animation, if you see it moving, it looks way better, right? You're not getting those Moyer pattern, you're not getting the jitter. It just looks quite nice, actually. Where am I? Okay, and then, yeah, okay, so we'll come back to that in a second. So that's pretty cool. Slide 31, 32. All right. And that might be the ugliest I've written anything today. All right. So, I showed you an example of a mip-map, but it's important to note that you can manually pre-compute them yourself, which is actually pretty cool because you can do artistic effects and make changes as the mip-map. You can manually pre-compute. But actually these days graphic cards generally do it for you. Just let it do it for you. It'll pre-compute using bilinear filtering. You're done. So mip mapping is awesome, but there are problems, of course, and let me talk about one of the big ones. The problem is choosing which one, and what happens when you're close to that boundary of one mip map and the other. What do you do? Okay, so what the problem is you get sudden visual change at the boundary of one mip map, okay, stage and another. Okay, so as imagine you're zooming, or you have a tile floor, you have one level, the next level, one level, until you go to another level. When you hit that new level, you can see that because it's getting worse and worse, and it gets a bit better because your window gets bigger. So you have a boundary where you see this suddenly, and you might have seen this in video games where you can see a texture jump. As you move. Okay, you see a texture jump as you move. Let's take a look at that. So I couldn't find a really good example of this, but here's an example of a scene, and what you see is, this is a mip mapping bilinear where you have a nice, but then you see the jumping where you hit a different, like suddenly you have these banding where you're hitting new levels of the mip map. So this looks better than it would have with nearest neighbor, it looks better than it would have with just bilinear, but you're getting this banding effect. And this is zoom in of what it looks like. And look how straight that line is. That's because that's the spot at which the game is choosing a different mip map level, okay? So you're getting this banding effect, and sometimes it's not done that well. So you get this boundary effect of where the one mip map matches the other one, and we gotta fix that, okay? Slide 33. Now, the way that we fix that is with a technique called trilinear filtering. Trilinear filtering. Now, trilinear filtering is just like bilinear with one more line, okay? So what we end up doing is we interpolate between layers of the mip map. Let's try that again. Okay, So we interpolate between layers of the mipmap. So if you can imagine, our mipmap is kind of like this, right? Is a top layer, and then you have a bigger one, you have a bigger one all the way down, right? So what, that shouldn't be a triangle. Yeah, so what you do is, you still do your, your 4x4, or 2x2 rather, your bilinear, cool, 1 line, 2 line, and here's my other one, so 1 set, 2 set. But what I do now is I do it on the corresponding spot on the mipmap at the next level. And I do the same thing I do by those 2 lines. So if I draw that out on the side here, you can see something like this. So I interpolate this way, and then I interpolate this way from my spot. I should probably mark the spot in there, hey? Like that. And then I do the exact same thing on the above texture. Yeah, I do the same interpolation. And now what I do is, because I know the distance between those mipmaps, I know my magnification level, I've already calculated that for the mipmap, I draw myself another line between, actually let's not use pink. I draw myself another line between those two, and I interpolate there to find the actual value of my pink. And what you get there with trilinear filtering is you'll get that smooth transition between one mipmap level and the other, and all you do is one more interpolation, assuming that you already have that calculated. Okay. So you can see here, this was a banding we get with bilinear. You go to trilinear and you get a much smoother result. You can look up other examples online, but because trilinear is so standard now, it's a little more difficult to find this comparison for you. I'll mention while we're talking about mipmapping, because we're done with the mipmapping section almost, is that here's an example that I came across. I grew up with Nintendo 64 and PlayStation, and people talking about which one's better, which one's worse. PlayStation had the CD, which meant they had awesome music, and they had a lot of storage and movies. But Nintendo 64 had the better graphics hardware. It supported mipmapping. It supported bilinear filtering in the hardware, whereas the PlayStation didn't. It was a cheaper hardware. So you can see this chunkiness in here, this chunkiness and the chunkiness of the rocks, whereas the 64 looks a lot smoother because of all that filtering that's going on. However, if you look at the PlayStation, the textures are much higher quality because they had CD-ROMs. They could put really high quality textures, and the fire looks really nice. Whereas the 64, because they didn't have the memory to put high quality textures in, despite the better graphics hardware, you have this blurriness, and and here, look at this. You can see the mipmap boundary right there. So they're not doing trilinear filtering, are they? Because you see suddenly the mipmap boundary is sharper and blurrier, and it didn't have a graceful boundary. So this is kind of cool to look at, the PlayStation versus Nintendo 64, and you can see the different kinds of graphics hardware that they used in that. Alright, so there's still yet another problem with mipmapping, but we'll take a break here and we'll come back and learn about it.